Good day, everyone. My name is Rebecca Lilly with the International Association for Energy Economics. It gives me great pleasure to welcome you to today's webinar entitled Global Liquefied Natural Gas Trade Under Energy Transition. We are grateful to Ning Lin and Robert Brooks for today's timely discussion. First, a little bit about the International Association for Energy Economics. We are the largest association specializing in the field of energy economics and provide a forum for the exchange of ideas, experience, and issues among professionals interested in the field. The organization produces two professional journals, a newsletter, and holds conferences and virtual presentations, along with a host of other products and services you can find at our website at iaee.org. If you're not already a member of the association, we welcome you to join. A few housekeeping matters in regard to today's webinar before I hand things over to our speakers. First, this webinar is being recorded for those that cannot participate in today's live event. If you have questions for the panelists, please click the Q&A button at the bottom of the Zoom window and type your question. We've allocated time at the end of the webinar to read and answer them. And now I would like to introduce you to Dr. Ning Lin. She is an energy economist who joined the Bureau of Economic Geology at the University of Texas at Austin in 2019, and Dr. Robert E. Brooks, who founded RBAC Inc. Ning, over to you.
Hello, everyone. I'm very glad to be here. Can you guys hear me okay? Okay. Yep. Good, thank you. So I will open up the webinar today. Very excited to be here and with my colleague, long-term colleague, Dr. Brooks, to present to you this webinar. So I'm going to share my screen. Okay, so the topic today is about global liquefied natural gas trade under energy transition. And I'm going to open up the webinar to tell you a little bit about our roadmap, what we're going to talk about. Since today we are doing the webinar for the IAEE, International Association of Energy Economics, we're talking to our fellow economists. So we figure that it will be better that we structure our webinar this way. So first, we're going to talk about some of the detailed technical modeling methodology of G2M2, which is our global gas market model, which is a platform simulator that we use to do the scenario planning for LNG, which we're going to present to you the results later. So the first part is techno-economics, modeling methodology. And the second part would be, we'll go through some brief section of current market conditions and trend, which it's important to address for, looking at projections of natural gas trade. And the last, we will present the scenario planning results of different natural gas and LNG trades under different scenarios, and we have done here for this study. So I'm going to hand over to Dr. Brooks to go through the first section.
Thank you, Dr. Lin. Okay, so first of all, I want to talk a little bit about the G2M2 market simulator for global gas and LNG. You can see on the screen different categories of attributes of this particular simulator and the database that goes along with it. Typically, this simulator is run with a monthly periodicity. We have historical data going back to 2011, and so we can run backcasts from 2011 forward. And our scenarios typically, in terms of long-term, would run out to 2050. We have over 100 countries are represented. I'll show you a little bit more about that in a moment. We also can represent in this platform gas of different kinds, natural gas and renewable natural gas, for example. Hydrogen and methane hydrogen mixes capability is under development. As far as demand is concerned, we separate demand by different sectors. So you see residential, commercial, industrial, electricity production sector, or the ELC sector, and transportation, TRN. We have a lot of information about LNG, which is the primary topic of our conversation today. So we've got detailed information on liquefaction or export terminals, import terminals with regasification typically, and contracts. I don't remember exactly how many contracts, but it's in the multi-hundreds of contracts that we have. And a number of pipelines around the world, most of which actually are in either North America or Europe. But we also have detailed on pipelines in other places, including Asia. China in particular has quite a pipeline system, and a number of other places. Over 600 underground storage fields. Again, most of these are in those three places: North America, Europe, and China. We divide LNG transportation up into a number of different tanker classes. So we explicitly represent the different kinds: Qmax, Qflex, and then the new ones that are being designed for the Qatar expansion. We just call that QNew. We have the Arctic class that is used for Yamal and other Arctic LNG2 when it comes into service, and conventional LNG tankers. We also have facilities for modeling the energy transition, which we're going to be talking a little bit about today, obviously, and CO2 reductions. So we handle renewable natural gas. We explicitly represent carbon markets and taxation, government mandates regarding CO2 and methane. And then, as I've said before, developing hydrogen and mixed capability. So in the end, G2M2 is a supply-demand balancing network, which includes pipeline systems and LNG infrastructure. Okay, so this is obviously just a simple map of the world by country, so you can see all the different countries that exist in the world. Most of these countries, not all of them, but most of them have some kind of natural gas, either consumption or production or both, and are included and represented in the model. However, there are some countries that can't be represented as a single node, network node, for example, because they are too complex and large. Their markets are too large, and it makes sense to divide them up. So there are about 10 different countries are divided up, and you can see Russia in the upper left, and China in the upper right. You can see United States below, India and Australia. We also break up Malaysia and Indonesia, and there may be some others as well. So the network model is, when you look at it from a single period of time, this is a generalized view of a network model. And this type of model consists of three different kinds of nodes. You might say we have supply nodes and the arcs associated with them. We have transportation and storage nodes that are in the center part. So you can think of this as the upstream, the midstream, and then the downstream here, demand nodes and demand arcs, where the demand functions are contained. But this is a multi-period model. It's not a single period model. So the different models such as this, these single period views, need to be linked together, and they are linked together through storage. So you could think of each one of these models like I showed just now. Here's one, here's the next period, here's the next period, here's the next period. This is just a little excerpt from it. And you can see they are connected together through storage. So you could say in this first system that gas is moving through space, whereas in this one, gas is moving through time, you can see, as it is staying in storage from the point where it's injected until the point where it's withdrawn later on. In our G2M2 model, we also have LNG, so liquefied natural gas, and we've got storage facilities here. So you can see it's not just underground gas storage, but also LNG storage that's represented in a similar way. Each supply curve in each period of time can be as detailed as you want. Typically, in any given period of time, a gas supply curve looks something like this, and you can break it up into pieces where in each piece, then you have a constant price elasticity. So the main takeaway here is that supply in this model is a function of price. The higher the price is, the higher the production capacity is up to a certain point. And so in this case, we've got Q2 is the maximum production that is possible, the production capacity. But if market price is lower, then the quantity that you're going to get is going to be less. So at higher prices, again, you get more production. Now, this is just a snapshot. And of course, over time, it can change. And so here's an example of the a set of supply curves that we have in the model that are dependent on price. So on the right-hand side, you can see the price that corresponds to each, the blue, the red, and the purple here. So this is a low price level. These are more like historical price levels here, and then these are future pricing possibilities out into the future. And you can see recent price run-ups here quite high in the US and of course much higher in Europe, but expectations that these prices will come down. And so we have three long-term prices here that are quite low, medium, and high. And each one of these corresponds to a different production profile going out in the future. So basically, this is saying that if prices are low in the market and maintain this low quality, you're going to peak out your production capacity soon, and then it's going to be coming down. Whereas if prices are in the higher range, your production peak is going to occur later. It will eventually occur at some point out in the future, but at a much higher level. The units on this, you can see this is in millions of cubic meters per year. And basically the way you can convert this, if you're in America or in North America, if you just look at the first three digits here and then divide that by 10, so get rid of about 4 zeros here, and that'll give you an approximate measure of this or conversion into BCF, or billions of cubic feet per day. So this is about 80 billion cubic feet per day along the top axis. And this is US dollars per million BTU in real terms. Demand curves, rather similar. You can have multiple segments of a demand curve. This is an example of a single segment demand curve, which has relatively low price elasticity. So even when prices get high, the amount of change in demand is relatively low, although here it looks like it is definite. You can also model in your demand curves fuel switching if you have a good idea of what some alternate fuel will be where you would have switching. This might be very useful in the future when we're talking about hydrogen, for example, or as one way that you can also have demand curves in a particular area where an alternate fuel like coal or whatever is predominant. So here's an example. The previous one in supply was the US West South Central census region. This is Germany, and you can see this is the electric sector. And so you can see, just as we had before, here's historically relatively low prices. But in the future here, we made this high price to be very, very high, as a matter of fact, just to handle situations that we hadn't even, I think anybody had really envisioned previously before this last year. But we want to be able to handle those kind of situations, as well as ones that are more likely down in this range right here. And you can see that in Germany, we have, looks like pretty much linearly decreasing gas supply under any price condition, although certainly when you have the higher prices, of course, it's a much greater effect on demand than if you have lower prices. But this is part of the gas phase out that Europe was certainly planning on prior to this last year. And as a result of the war between Russia and Ukraine, They may be, to some extent, rethinking what the future of natural gas is going to be. In this particular scenario, we're taking their prior view, which is pretty drastic reduction in natural gas over time. But with G2M2, you can do all kinds of scenarios where you assume sort of business as usual. You can have deep reductions in certain areas. You can have even increases in demand over a period of time, such as we expect in certain parts of Asia. Okay, so how does the model work? Well, the model, as I said before, balances supply and demand. We also call this market clearing. The usual case of market clearing in an area or a market would be where you've got some kind of a supply curve represented here. We've got some kind of a demand curve as represented here. The point where they cross is the market clearing price and the market clearing quantity. And as we know from our microeconomics classes, this is equivalent, if you will, to a maximization of a concept called consumer surplus and another concept called producer surplus. And it's the area under the curve, to the axis on the vertical axis, which is the price axis. So this area right here is maximized when you find the point where these two curves cross. Okay, but we have something a little bit different here typically, and that is that production occurs in an area that is, or a region that is different from where consumption occurs. And so in this case, you need to move your product from one place to another. And so we get what we call spatial equilibrium. And we have a very similar kind of a diagram here over on the right-hand side. But the point where the two curves cross is not a single point, actually. It's not the market clearing price because you have to take into account transportation costs. And so if this is the price of transportation, you can see that you actually end up with two different prices. The clearing price in the supply region, the clearing price in the demand region, and the difference between them is this transportation price. And we still have a producer surplus and consumer surplus, which are maximized, again, given this particular circumstance where we've got a network, simple one, two nodes, and one arc linking them together with a supply arc and a demand arc. Now, you can have situations where your transportation is constrained. You don't really have enough transportation to satisfy the condition that you had before. In other words, the amount of production that is desired and the amount of consumption that is desired. So you can have this constrained situation, and this is represented here. So this is the unconstrained, here's the constrained, and you can see your producer surplus is less, your consumer surplus is less, but also your market clearing price in the supply area gets reduced or diminished, and your market clearing price in the consumption area gets increased. So these little differences between what that original price was and then the constrained price we call rent, economic rent, and you can see there's two pieces of it, one piece here and one piece here. The sum of those is the total rent that can be associated with the constraints in the market. So all of these things need to be modeled to be realistic, because in a realistic market model, you do in fact have limits on how much transportation capacity that you have. So the more exacting model, you might say, of how G2M2 works. We have divided the world up into what we call geopolitical units. Those geopolitical units are mostly at the country level, but as I showed earlier, we also have these sub-country areas, such as in the United States, Russia, China, India, and so forth. And so each one of those is called the geopolitical unit. I showed you an example of USA West, South, Central. So we've divided the US up in essentially into the census regions within the US, although it actually gets divided a little bit more, but approximately by that. So each one of these GPUs then has this model associated with it. So you have gas production potentially, depending on the GPU in the West South Central District, you have gas production into this GPU. It moves over into the consumption area. It moves gas across pipelines into consumption. It may also move exports to other GPUs, such as the mountain area, and then towards the Pacific, for example, is a very typical one. But it also might take some of that gas and actually move it to liquefaction terminals for LNG exports, which we know also happens in the West-South Central area of the US. Finally, it could also go into gas storage. So you can have this gas that has been produced could end up in gas storage and then withdrawn later, as we showed. And you can see how that flows. If it's withdrawn, then it moves through the pipelines again to get to either an export to liquefaction or consumption. In addition to gas production, you can also have pipeline imports into the GPU, or you can have LNG imports, which go into local LNG storage and then regasified into the market. The West-South Central does have the ability to import LNG. However, that's not the activity that takes place now. Used to take place before the shale gas revolution increased, made possible production levels, and companies took advantage of that by building export terminals for LNG. So this is the most complicated model that you could get. Some GPUs are much, much simpler than this. For example, Japan doesn't have gas production, so it wouldn't have this. It doesn't have pipelines, so it's not going to have pipeline imports. It's not going to have pipeline exports to other GPUs. It does have local pipelines to move within the GPU, and it does have consumption, no gas storage. It does have LNG imports. That's how it gets its gas, from LNG imports that move into Japan and then primarily are used for consumption. So a pipeline model looks something like this, so similar to that network model that we had before. We've got supply links where gas is received into a pipeline. It moves from one segment to another segment. Here, the segment is a GPU wide, you might say. So a pipeline segment is the pipe that exists across the segment, across the GPU. And then here's a second segment, a third one, and a fourth one. And then this is the handoff to a different pipeline, pipeline B, and a segment here. You can have demand at each of these different locations. So this is representative of how our pipelines are modeled in this simulator called G2M2. For LNG, of course, it's a little bit different. You don't have the various sort of transmission points, you might say, between different areas. You have just simply origin to destination. So these are LNG export terminals. These are LNG import terminals, origins, destinations. And the flows can go from each of these depending on what the contracts are and whether that LNG can go to companies that can deliver it to multiple different terminals or so forth. So all these different pieces that I've showed you are tied together. We've got supply functions, pipeline models, LNG models, demand functions. All of that is contained in the database for G2M2. And the user can establish these according to the needs of the particular scenario that the user is attempting to model. All of that in the database, then there's a user interface that the person uses in order to pull those scenarios together and then to launch off the computation of the solution, which would be to compute the actual production levels, actual consumption levels, actual flows on pipelines, actual movements of LNG from origin to destination, and so forth. So this is representing essentially that program, the scenario generator, and then the launching off to the solver. So the solver that we use, we have both used Gurobi and CPlex to solve this model. Works pretty much equally well for both. And then we do have an intermediary program in which we build the mathematical model, and that's called AMPLE. You may be familiar with it. So we essentially take our scenario and we send it to Ample. Ample sends it to Garobi or Cplex. The model is then solved and then the results sent back to the database. This is the input part of the database. This is the output. And so we've got various visual analytics that are associated with this, both in Microsoft Access, can be sent to Excel, and then also Power BI. So we've got all of those things. You can see here's a representative sample of different kinds of reports that you can get. So I think that that's it for me. And now I'd like to hand the control back to Dr. Lin.
Okay, well, thank you, Dr. Brooks. So I think that by now, I hope that you get a fairly good, decent idea about how the basics and the structure, which I think is important for our economists to understand how the model kind of come together. I'm going to spend a little bit of time talking a little bit more about the model because this is a part I think is quite important, especially relates to energy transition. So Dr. Brooks mentioned about demand curves, and in the model there are demand curve for each period for each node on the network, but the trajectory of the curve, the groups of curves going over time, also are part of the inputs. Is really something a modeler has to decide or to model, and that is something is becoming critical in the past couple of years. That's one of the things I have been saying the past couple of years is demand uncertainty rules, because in the world right now is, since the beginning of pandemic, and then, we saw what happened, and then there is 2022 with geopolitical risk, and even more so looking forward is a lot of government, energy transition policy and its impact on the gas. So this is kind of present a question is, although the G2M2 model originally designed is the user, the analyst, or the modeler could model what will be the trajectory with demand. But, this is a part that actually the model provides some additional modeling help to say, can we explicitly integrate those conditions in? For example, this is the ones that, we have been struggling and trying to model. For example, macroeconomics condition, for example, inflation, recession risk. Another one, alternative fuel prices. How about coal to gas switching? How about the competitiveness of renewables versus, natural gas? Another one is decarbonization policy, or the policies the government has, and how do we model and basically impose, really the policy targets with its impact into natural gas. And of course, another one is weather. Weather is generally, here we're talking about is really short to medium term. Winter, for example, because it's a monthly model, so we look at volatilities and the impacts of the weather on different key markets, in Europe versus Asia and North America, which we have seen some of those type of impact in the market in the past couple of years. And the very last one is how to put in hydrogen or other renewable gases to competition with natural gas. So all of these are kind of what we call on the demand side uncertainties, because these are the things is going to play out and impact demand. So I want to spend a couple of slides talking about how G2M2 models its demand side and kind of give a little bit more modeling support for scenario planning. Sorry. Okay, so for the demand trend, like I said, we're trying to cover how to determine the trends for the demand curves to move over time. In the model, currently there is coverage of 182 countries that actually defined with demand in sorry, let me just move my cursor for the G2M2, and in the chart you can see the map, you can see the coverage and the number of countries for the demand outlook. Most of the country that in the blue color is the demand is down by regression. while the red ones are by growth rate. And the reason why is, as many of you that have done demand forecasts before, is even sometimes we can find the data doing regression or different type of regression. The results sometimes, first of all, may not be satisfactory, and we don't think it's reasonable. Maybe there's a shift of the country, or maybe there's limited historical data. So there are some of the countries in the end, based on comparing the regression and the growth rate scenario of how to project the future trend, some of the countries actually end up using a growth rate scenario versus using regression-based results. But by the way, this is something that the G2M2 model provides as a base case, but the analysts, like for example, for me, I can choose whatever the regression or growth rate I like to redo and customize my demand. On the non-electric part, because there are 5 different sectors of demand: residential, commercial, industrial, transportation, and electric. The first 4 parts, residential, commercial, industrial, and transportation, are done for regressional analysis, basically using a log form regression, links those to the macroeconomics variables. And that covers about 100 countries, right? 103 countries with regression covering. And that actually, although it's not all the countries in the world, but in terms of volume, that covers almost 80% of the total non-electric gas demand of the world. So I think that's a pretty decent coverage. And this is just a very simple, illustration. This is basically the model theoretical form, which is, it's actually a very classic Cobb-Douglas, demand utility function derived, which would have, representation on elasticity as well as macro variables, which will be regressed on the log form. And this is a list. This is a list of the type of variables that are used for calculating non-electric demand, which including GDP, population, urban population, labor force, and different sector of GDP. Those are mainly trying to focus on forecast the industrial sector, because every country's industrial sector is different, which ones are using a lot of natural gas. Some countries are really tied into petrochemicals, and some countries tied into manufacture or textile and food industries. So that actually changes how the trajectory of the industrial demand. And the other sector that is quite interesting and, worth a lot of attention, I think, is on the electric generation side. So gas demand for electric generation. For this part, the model is the G2M2 model, the electric sector differently. So there are currently 110 countries covered in the models builder, and it is covering about 90% of the total electric demand of the world. And in order to model the gas demand for electric generation, as many of you can understand, that it's actually modeling the electric market. So we actually not only just focus on gas anymore, we have to include other competing generation technology like coal, natural gas, coal, oil, hydro, nuclear, and renewable, which is solar, wind, and others combined. And the methodology, what we use here is really looking at a levelized cost of electricity, and in terms of competition among different generation technologies. And the model form that we have adapted here is a multinomial logit model, which to forecast a market share. Well, technically speaking, is a multinomial logit, is a nested logit model to look at the marginal generation cost, which includes, if you use a fossil fuel, you will have your fuel price and carbon price. If it's non-fossil fuel, you have levelized the cost of electricity as well, but it just doesn't have fuel. But this is where that it's possible to explicitly to model the carbon price as part of the cost of generation. And this is just a illustration of the market share estimation by technology, the model behind it. And the multinomial logit model is estimating the market share of each of the generation technology based on the marginal cost of generation. And this data, this is this, of course, as any of you know, if running such a model on a country level, it will require a massive amount of data gathering. So this is once it has its own database of all data of which I can actually show you. It's all the data that use, not all actually, it's only the major part of the data gathered for this model. It has power generation by technology, installed capacity, electric load by country, so that is a demand of electricity, capacity factor calculated based on historical data, and retirement rate by different technology, and fuel prices. And like I said, the levelized cost of electricity, we use a couple of majorly published reports, including ARENA and also Bloomberg reports that they do regular publication of levelized cost of electricity, and of course, and also carbon price and emission rate to calculate what's the impact of carbon price on fossil fuel. And then one of the last one is policy targets, which is quite important because besides all the market and the levelized cost, there is also a factor that policy and targets could influence materially of the generation mix. We give a good example of this is on China, right? For example, if on the left side is a base case of China, a current generation mix going forward without any targets, right? So we can see each of the sector grow, and coal is also growing because coal is relatively cheap and, or is at least competitive as what we see going forward. And if we say, well, China is, this is, by the way, just hypothetical, but, we can do this for Japan and Germany for the past couple of years. They all have very clear, stated goals. But here we're just taking the example of China. If we say we want to do nuclear 15% by 2040, coal 10% by 2050, the model actually has algorithm to automatically calculate based on market share results and superimpose targets based on the target deadline year for each of the technology to recalculate the mix. Once we recalculate the mix, you will know what would be the result natural gas demand for this country, for example, China. In this case, if nuclear 15% and coal 10%, which is not a very ambitious plan for especially nuclear, right? For China, we can see that natural gas would have a huge amount of growth in that scenario. So after looking at how the demand, is modeled in G2M2, I think I'm going to switch gear to talk about the market condition briefly here, so I can show you some of the scenario planning results that we have done using G2M2, because these are a couple of the trends that, kind of mirror to what I and Dr. Brooks have just shared of how the G2M2 do the modeling. So for internal market dynamic, I don't think I need to spend much time to talk about the natural gas market, what happened in the past, 2 years. It's a pretty dramatic year. We can see that European price shot up, especially in year 2022 after the, Russian invasion to Ukraine, with geopolitical, events create a huge shortage for Europe's gas demand. Cutting down Russian supply. And this is monthly pipeline data for the EU 27 plus UK. And we can see that, all the Russian source of imports that is dramatically coming down through the course of 2022. Which I'm sure that this is something that everybody is quite familiar. I've seen many charts. Another thing, quite importantly, is it's very important, especially for a model like G2M2. It's not just the pipeline balance, it changed because G2M2 actually models on a pipeline level. So what actually happened, what we observed based on the monthly data, actually not just monthly, we have daily data on NSOC all the way, to yesterday if we want to. What we see is not only the balance have changed, it creates a lot of constraint in the European market because one time the change of the flow on the mass balance base, there are a lot of change of directional flows creates pipeline constraints, and which also contributed for the price high volatility and the price spikes in the market. And you can see this is a chart which shows, the blue color is LNG coming into Europe. The green arrows are the, positive increase of pipeline flows. We can see there's a Turk Stream and TANAP and some of them from North Africa, but we also see the, some of the negative flows, which is a reduction of pipeline flow, which comes, mainly from the Russian side of the 3 main routes from Russia to Europe. And those are the things that can be demonstrated and shown, which I think that contributes how model can calibrate pretty well with historical events. In terms of, these are the market conditions that is, it's being included and calibrated for the model when we are looking going forward. But there's a couple of other things I think to point out that when we're looking at the outlook of LNG going forward. One of them is to recognize that what happened in 2022 and in the past 2 years, it's not just an energy crisis. It's really, it's really an economic and inflation crisis. That's what the IMF has coined, is saying it's an inflation crisis. Because if you look at this chart, which I find it quite interesting, is this is a chart plots the percentage of countries with annual inflation rate greater than 6%. I first saw this from the IEA's World Energy Outlook presentation, which I think is fantastic, because it really illustrates the point of energy crisis, much greater than natural gas market. Because if we see right now where we are of 2022, is energy crisis is almost 100% of the countries. Almost 100% of the countries in the world are experiencing higher than 6% of annual inflation rate. And the last time we saw that was back in 1970s with oil crisis. So this is pretty shocking. I mean, I knew that we all experience inflation, but I did not know this much till I see the data. And a couple of sectors that it's really driving up this phenomenon we have on the left-hand side, which is energy and agriculture and metal. Those are the sector of commodity index that we can see is a main driver responsible for the inflation. And on the right-hand side, it shows what is Russian and Ukraine's share of these commodity exports. And you can see that the percentage, which is showing on the vertical axis, is there is a large percentage of global exports coming out of energy and metal and mineral and foods, which just associated with the country that in the conflicts or affected by the conflict, which is Russia and Ukraine, and there is a little bit of Belarus here showing for the metal. But that's what is really something it's kind of initiated and caused this this run-up of inflation. But it also says that it will not go away right away, given what we see of the political situation. We see this inflation, unfortunate and constraint of the supply chain for a global commodity, major commodity category, is not going to go away very quickly. So with that a concern of run-up inflation, as well as looming concerns of recession, what we have seen on the government side is all the spotlight is on the government for 2022. There is a lot of government movements and policy, which is very critical, especially when we're doing gas trade of modeling for the future, because a lot of them has a material impact on natural gas market. And the question is, how is that going to happen? And there is a couple of the government policy that are listed here from US, the Inflation Reduction Act, which passed in August this year, and the European Union's, Repower EU Act, switching, away from fossil fuel to renewable and really work on the energy efficiency. India also passed a pretty important Energy Conservation Act this year as well, to focus on renewable and also buildings and appliances energy efficiency. They also have decided to go ahead to set up a carbon trading platform, and also Japan that is moving forward with their green transformation plan, which is going to restart their nuclear, which also is going to have a pretty big impact on natural gas. So I think these are all very positive things for energy transition, because government clearly is trying to leverage this crisis, but it turned into a pivotal point for energy transition. But, like anything, there is a great intent of doing this and create market momentum for our energy and economics system and create jobs, but there are also risks of these government policies. There are a couple of them that I listed here, from my personal view. One of them is the inflation, right? We're doing it as a high inflation period. So the inflation will directly offset some of the investment returns right away, and that would risk to have stagnation of some economies if not successful. And the second thing is most of the policy here is picking winners and losers based on their technology. And that may remove some headroom for competition of emerging technology. For example, in natural gas, right, we also have a lot of innovative technology and improvements, which may get some headwind. And of course, on top of that is all the policy is requiring a high level of commitment and fast deployment of labor and regulatory support for those to happen, which that means when we are good modelers to look at in the future, we have to be pretty realistic to say, these are the target, but what is the implementation risk? How likely these things will happen and will hit the target as planned. So with that said, I think that you will see we kind of bake those factors into the model. The very last slide before we show in the model results is on trend of energy investment, which is quite interesting. One thing I want to point out is there is a lot of low carbon energy investment in 2022, but it doesn't mean there is no oil and gas investment. So in 2022, there is oil and gas investment as well, increased, as well as for low carbon energy. Based on IEA, there is 1.5 to 1 ratio currently for low carbon energy investment versus fossil fuel. But of course, with the government policies, the ratio is going to expect to grow. That means it's going to be harder to push through large capital project of oil and gas through. So with all that type of trend that we think is quite important material for the markets, how do we look at different gas scenario? With all the uncertainty ahead, obviously, I think that one scenario is not going to cut it. A base case and status quo is not going to cut it. So what I want to present here is we're going to do 3 scenarios. And what we're doing is we're taking a base scenario of 22Q3, what we call the latest case that is provided by the G2M2 platform. And what we did is we take the demand multiplier and shifting demand curve based on IEA scenario, which I'm going to show you in the next slide. As you guys probably have already seen that IEA has published their latest World Energy Outlook in October, right, just last month. What this model we did is we thought it would be a really good exercise to go through taking the IEA's state policy case, their STEPS case, and also their APS, which is announced pledge scenario. We take the 2 cases, which reflects different degrees of government policy and quite a bit of material difference of demand projection. And we use those cases to re-modify the demand projections we have in the model and rerun the model and see what are the responses of the model, what type of validation insights we can gain. So the model we have on the left, this is just kind of overall output, is we have a status quo, the base model that we started with actually a modest growth of natural gas consumption. Which is a blue line, the base case, and we have the pink and red, which is basically a customized scenario following IEA's assumption, which I wanted to emphasize here. We're just following the IEA's assumption on demand. So what it means is we're taking the demand output as a multiplier to trying to align our trends. So basically, forcing the demand curve as saying these are the trend of the demands going to behave in the long term, but we're preserving the price responsiveness in the market itself. So what it does is it's leaving room to the market to respond to these targets, these intended targets, and that will make the scenario result a good validation tool to infrastructure shift and bottleneck, or maybe even balancing needs, right? So if there is a huge type of shift in one country, let's say it's short of supply and it cannot happen, the model will indicate what type of additional imports needs and which will signal through its local price. And for those who are not familiar with the IEA case, the IEA steps case is really the stated policy. IEA state that this is where they will have all the policy that is passed. So all the 2022 policy passed, for example, US IRA, the European policies, as long as it's passed and stated by sector, in this model, the pink line, it's assuming all the government passed acts and policy and targets will be met 100%. Okay, and the red case is saying, even on top of that, there are low emission gas and hydrogen segments is going to be scaled up, as well as there are pledges that the government has announced, even without concrete supportive policy, that's the ones that the scenario, if the government will do all this of state policy, and on top of that, pledge the emission targets, if it's reached, what that will look for the gas. So it's an even more aggressive case in terms of energy transition. So this is a three, scenario showing the spectrums of the difference. If we go on to see some of the results, this is just breaking the gas consumption changes by different regions. So this is showing a panel of 8 regions that is showing for the G2M2 model. And we can see that no surprise that we see quite a bit of the reduction, especially across different scenario. I think that for Asia was quite interesting. There's a huge difference in terms of the steps policy and also the government announced the pledge scenario, because there is, for Asia, I think that all the state passed policy and where the pledge target is quite a bit of difference. That's why you can see there is a huge amount of the impact on the natural gas demand in total. Another one, we see the similar, trend in North America and Europe as well. This is showing the gas consumption change by sector. So we can see that in the total, the world and broken down by some major regions as well. And I think one of the, key takeaway from this is, the electric sector is probably the ones that has the most of the impact through different energy transition policy as it's switching away from natural gas to other generation technology per government policies. But industrial sector is one of the hard to abate sectors, and so we see a relative, inelasticity in the industrial sector across different scenario. And since this talk is really about LNG or gas trades, what's the difference? So I'm going to show you a couple of the slides, just really focus on the LNG market trade. This one is on liquefaction, and on the left side, we're showing the 6 key regions of exporting of natural gas by each scenario. And the right-hand side is exactly the same information, but we're showing it based on forecast change from 2022. So it's just showing it in different way. But one thing it's quite interesting I want to point out is you see the difference and how different government policy and energy transition process is going to impact the liquefaction potential by different markets. One of the quite interesting I want to point out is kind of the North America. North America definitely see some robust growth, but one of the things I think is quite interesting from the G2M2 model is showing that North America have that kind of a drop around, I think it's 2027 to 2030. And that is really reflecting that although there's going to be a quick ramp up, but once Europe stabilize, it's, and also moving away from natural gas, we will see that there is going to be some pushback, some loss of LNG export needs, from North America. And on the import side, I only chose 2 regions. One is in Asia, one is in Europe. And here we're not only just showing the LNG, which is showing in the lines, we're also showing in columns of pipeline imports, because both the key regions of importing natural gas, Asia and Europe, they both do, have pipeline imports as well as LNG. And one thing is quite interesting, I just wanted to say 2 points on this is, everybody this year is focusing on Europe, which Europe is quite important. It has a very influential, events which impact the whole global market. But one thing about LNG, when you look at these two charts side by side with the same scale, one thing is pretty clear, is Europe right now is have a short-term, short position of LNG, but Asia is really, if we're only talking about growth and incremental value of LNG, Asia still remain to be the main market. So, a lot of talks about, as Asia's economy rebound and China reopening in next year, there's going to be even more competition because Asia is, has quite a bit of potential of LNG imports. And another thing we also see is that pipeline imports into Asia. That's a lot of them, from Central Asia as well as Russia. And when we go into even a little bit more detail in the last couple of slides I have here is into LNG imports. One of the really neat things of G2M2 model is, taking the IEA case, which is quite interesting, lots of interesting scenario. But if we're really interested about LNG, we really want to ask the question that how the energy transition policies it's going to influence different LNG trade flow patterns. And that is a level of detail and granularity that at least, I couldn't see for the published report of IEA from the World Energy Outlook. But, so we wanted to dig further to really understand how that means for different country level competition. So this is actually a flow chart of LNG flow into Europe. On the left side is, looking at IEA STEPS case, and on the right-hand side is looking at an APS case, which is a more, aggressive case of energy transition. And the yellow line on the top is a base case, basically from the status quo case, which is the base case that, we started with. And you can see that when apply different energy transition scenarios, we can see that there is less imports. First of all, in total levels, it's less LNG import into Europe. And we can see that the peak really happens in about 2020, in the next 3 to 5 years, let me say. That's probably the right way to describe it. And if we take a look at the bottom chart, this one shows by different origins of, here is by region, but we're pretty clear knowing which country that would be, right? So we have changes of LNG flow by the source countries. And we can see basically the punchline is as Europe moving away faster for energy transition, who are the ones going to take most of the impact? First one is going to be North America, which is really the LNG coming from the US. It's really truly the marginal tier of LNG into Europe, but we also see that there is going to be some impact on Africa, right? As well as I think is a little bit of, so there is a little bit of Middle East and from Qatar as well. And there are some of the Africa, but I think the main story is the highest impact part is really from US. And there is some in Russia as well. If you can see that there, in this model, we still assume there is continuous LNG flow, from Russian LNG into Europe. And this is a similar setup of the slides, but it's LNG imports into Asia. And that's quite interesting because I mentioned that Asia is still a larger market for LNG in the future. And so with the whole world moving at a different pace of assumption between different scenarios, it's interesting to see who is to gain, who is to lose for Asia markets. And one of the things we see is the bigger mover part here for Asia as the energy transition, I will say, is Australasia. So Australia is really the ones going to have the marginal tier of reduction of LNG demand in Asia as Asia move, as the world moving faster into, energy transition. And we see also there is some reduction of Middle East. So this is a kind of a different picture. So Middle East and Australasia is really the regions going to have most of the, reduction of LNG trade in an more aggressive energy transition case. And, we landed back into US talking a little bit about, this is looking at a different one, is actually LNG export from US. I'm sorry, I said import is actually LNG flow from US. And a similar setup, we can see that the LNG flow from the US by two different cases. And what we can see is here, all the differences is indicating destination regions. So with different energy transition, how US LNG's flow pattern changes. And no doubt, the biggest driver of the difference is on Europe, right? And we can see that, there is quite a bit of reduction on both cases for Europe. But what is quite also interesting is, first of all, I wanted to point out there is some incremental increase for Asia. But like I said, if you see the slides before this, you will know that US is really, not, as a major player compared to Middle East and Australasia in Asia in the future. So we see less of an impact in total for LNG exports from US between these cases for its destination changes in Asia. But we also see that there is some potential increase of Middle East, imports LNG needs from the US as well. So the very last slide I want to show in terms of the results is actually natural gas prices. The reason why this one is interesting is the G2M2 model will take the demand as assumption of trajectory and solve the model. So we will solve for a natural gas price, while what we are also plotting is IEA's report's input assumption of its own natural gas prices. What we're trying to do is trying to look at what IEA has as a price assumption to solve for demand, and we're kind of doing the reverse order. We're taking the demand as assumption, solve for prices, and we kind of want to see that how different those two approach end up on prices, right? So we can see that actually, I think in total, in the overall things for 3 regions and 3 index, we're pretty similar. I wouldn't say that we're materially different, but what I will say is quite interesting is G2M2 model has shown that, a slightly lower trajectory going forward in the next decade. But we definitely see that as the market, especially more aggressive energy transition progress, natural gas market, if it's really shrinking size, it's going to put upward pressure on prices in all regions. So this is conclude my presentation, and I'm going to stop share for a little bit because I would like to see if there are questions and how we're doing with time. I think. So I think that I'm going to answer some of the questions we have. We got a question.
Dr. Lin, can you hear me?
Yeah.
Yeah, thank you very much for that. I think that I'm not quite sure. I think we're past the top of the hour here, so I'm not sure if we have too much time that we can actually answer questions live. I did try to answer while you were speaking, try to answer the other questions that came through. So, hopefully that will handle that. One of the questions was, can users or can attendees get copies of the presentation? As long as that is okay with IAEE, it's okay with me, and if it's okay with you as well.
Yeah.
Okay, so I don't know how IAEE and would like to handle that, but
if you'd like to email me the slides, I would be happy to post them.
Okay,
that's
good.
great.
We can certainly do that.
We can definitely do that. And I think, thank you. I think that a lot of slides is being answered already. So I guess if we don't see any more questions coming up, I think there's one. Okay, the open question actually. Okay, so that's not a question. Well, thank you. So I think that, Rebecca, I'm going to turn it back to you since, we're kind of past the hour, so I don't want to hold everybody for any longer.
Well, IAEE would like to thank both Ning Lin and Robert Brooks for an outstanding webinar. This webinar will be available on IAEE's website for future download. If you're not a member of IAEE, we encourage you to join by visiting www.iaee.org. We thank you for attending, and I officially close this webinar.
Thank you.
Thank you, Rebecca.